Hello students, we are discussing chapter 14 Oscillations part 2 today. So in part 1 we dealt with periodic motion and simple harmonic motion. What is meant by simple harmonic motion, etc. So here we are going to details of simple harmonic motion. So the first topic here is simple harmonic motion and uniform circular motion. When a particle executes circular motion, the projection of the particle on the diameter of the circle will execute simple harmonic motion. So that is what we are going to explain today. So if you look at the diagram, you can see a circle, a particle P which is executing simple harmonic motion in the anti-clockwise direction. Its angular velocity is omega and the radius of the circle is a. So when the particle is at P, that is the starting point, it makes an angle phi with the positive x-axis. As it proceeds in the anti-clockwise direction for a time t, then it makes an additional angle omega t, so that the total angle with the positive x-axis becomes omega t plus phi. Okay, now let's see. The projection of the particle P on the diameter x-axis. X-axis there is a diameter, y-axis also there is a diameter that is drawn. We are referring to the x-axis diameter. So you can see in blue dotted lines the projection of P, that means the perpendicular line drawn from P to x-axis is PP dash. That is what we call as the projection of the particle on the diameter is PP dash. So the displacement vector here is OP dash. OP dash here will be represented by x as a function of t, xt. So as the particle P proceeds with its circular motion, then OP dash also increases and comes back again, decreases, then goes to the other side of O, and then again it comes to the center and it comes back again. So it will execute oscillations as the particle P proceeds in a circle. This OP dash will execute an oscillation or simple harmonic motion. So we have the initial position vector of the particle is vector OP, and that is at t equal to 0, what I have been explaining. Then an initial angle is phi, but after a time t seconds, the angle made will be omega t plus phi. So the displacement of the particle or the position vector OP dash will be represented by the equation x as a function of time is equal to a cos omega t plus phi. Here a is the radius of the circle, then omega t is the angle covered in a time t seconds, and phi is the initial angle the particle already makes with the x-axis. So we have a conclusion. If P moves uniformly along a circle, its projection P dash on the diameter of the circle will execute simple harmonic motion. Now if there is a displacement as a function of time, then there will be velocity as well as acceleration for the particle which is executing simple harmonic motion. Here we have a circle and this is a positive x-axis, the particle at the point P here, and it is moving in the anti-clockwise direction. At P you can see the arrow mark represents the velocity at that instant. So the velocity here will be acting in a tangential direction, and you know V equal to omega into radius. When a particle executes circular motion, we have a formula V equal to omega into radius. So here we can see the projection of velocity on the x-axis will be lesser than the projection of displacement on the x-axis. Okay, so the velocity as the particle moves in the outward direction, as p dash moves in the outward direction, the velocity will move in the inward direction. It will act in the opposite direction. We will try to work this out mathematically. So here I have the same diagram drawn out again. We have the particle P, the projection of particle P here, P dash, and then we have omega A, which is the velocity, and this is the projection of velocity on the x-axis, and this is acting inwards. So velocity will be opposite in direction. So velocity is V into radius. Here the radius of the circle is capital A. And we have therefore velocity as a function of time is equal to minus omega A sine omega t plus phi. Now this formula we obtain by differentiating x with respect to time. If you differentiate d by dt of xt, you will get minus omega A sine omega t plus phi, because xt is a cos omega t plus phi, as we saw in the previous slide. Now this negative sign indicates that velocity is acting opposite to the direction of x. Now when there is a velocity which changes with respect to time, then there will be an acceleration for the particle which is executing circular motion. So the instantaneous acceleration or the acceleration at an instant of time t is given by differentiating velocity with respect to time. So it is d by dt of vt. And if you differentiate the expression for vt, this one with respect to time, you get acceleration is equal to minus omega square a cos omega t plus phi. But a cos omega t plus phi is x t. T in brackets indicate that x is a function of time, xt. So minus omega squared into xt. So velocity and acceleration have negative signs showing that they are opposite in direction to displacement. Now this is represented graphically. You can see the first graph, displacement versus time. So the displacement is represented on the y-axis. O represents the center or the mean position of oscillation, plus A is one extreme position of oscillation, and minus A is another extreme position of oscillation. So the total time period is capital T, and this T is divided into T by 4, T by 2, 3T by 4, and finally T. So if you consider xt equal to a cos omega t plus phi, and you consider here t, small letter t equal to t by 4, then we get 0. You get cos 0. Sorry. Here we get cos 90 pi by 2. So we get displacement to be 0. Here when omega t is 0, omega t is t by 4, or t equal to t by 2, 3t by 4, and capital T. You have variations of a, 0, minus a, 0, and again plus a. So this is the graphic representation of displacement versus time. It is sinusoidal in nature. Let us look at the second one, velocity versus time. The expression is minus omega a sine omega t plus phi. Here also you get t equal to 0, t equal to t by 4, t equal to t by 2, t equal to 3t by 4, and t equal to capital T. So your graph varies because it is varying according to sine function. So for t equal to 0, sine 0 is 0. Here we get sine 90. minus sine 90, so we get a negative a minus omega a, then you get 0 plus omega a, and then finally 0. And the third is acceleration versus time. So similar to displacement and velocity, you can work out minus omega square a cos omega t plus phi. Give different values for t, like t equal to t by 4, t by 2, t by 3, t by 4, and finally t. You get your expressions of cos as cos 0, of course, you know, has a maximum value 1. Cos 0 is 1, cos 90 is 0, and so on. You get a curve. So these are the graphic representations of displacement, velocity, and acceleration with respect to time. Next, we have Force law for simple harmonic motion. So as you see, using Newton's second law of motion and the expression for acceleration of a particle in simple harmonic motion, the force acting on a particle of mass m, you know, F equal to ma, the formula in Newton's second law. So that is written here as force as a function of time is equal to mass into acceleration. Alright, so acceleration is minus omega squared x, minus omega squared x as a function of time. Alright, so if you write m omega squared as k is called spring constant. If you write m or force constant, if you write m omega squared as k, then you can write ft equal to minus k into xt. This is x as a function of time, or where k equal to m omega squared. So what is omega squared? Omega squared is k by m, and omega equal to square root of k by m. So force is always directed towards the mean position, because force is also has a negative sign there, F equal to minus kx. So since force is always directed towards the mean position or the equilibrium position of the oscillating particle, it is called restoring force. Now simple harmonic motion can be expressed in two different ways. The first one, x as a function of time equal to a cos omega t plus phi, and force as a function of time equal to minus k into xt. Here force is linearly proportional to x, directly proportional, but it is opposite in direction. So magnitude of force increases when displacement increases, but its direction is opposite to displacement. And a particle which oscillates under such a force is called a linear harmonic oscillator. Next, we will see what is the energy in simple harmonic motion. The oscillating particle has got both kinetic energy and potential energy. So kinetic energy is given by the formula half mv squared. And we saw the expression for v equal to minus omega a sine omega t plus phi. When you substitute that, you get kinetic energy equal to half m omega squared a squared sine squared omega t plus phi. And of course, you know m omega squared is force constant k. So when you make the substitution, you get half k a squared sine squared omega t plus phi. Now kinetic energy is also a periodic function of time, because we have the omega t factor coming into the formula. And if you see, k, the kinetic energy will be 0 when the oscillating particle is at extreme position, or its displacement is maximum when x equal to plus or minus a. We see that the kinetic energy of the particle is maximum. And kinetic energy will be 0 when displacement is maximum. A correction there. Kinetic energy will be 0 when displacement is maximum or when the particle, oscillating particle, is at extreme positions when x equal to plus or minus a. And kinetic energy is maximum when displacement or when the oscillating particle is at the center. The center position is called the mean position or the equilibrium position, and displacement will be 0 there. What about potential energy? Now potential energy is given by the expression U equal to half kx squared. Alright, so for a particle in simple harmonic motion, U as a function of x equal to half kx squared, and x is given as a cos omega t plus phi. Therefore the expression becomes half ka squared cos squared omega t plus phi. Potential energy is also a periodic function of time because omega t comes in the expression. And potential energy for an oscillating particle is 0 at the center. And the center is represented by x equal to 0. And potential energy is maximum at the extreme position when x equal to plus or minus a. Exactly opposite to the kinetic energy. So acceleration is linearly proportional to displacement but acts in the opposite direction. Now what is the total energy of the oscillating particle? It will be potential energy plus kinetic energy. So when you write the two expressions and add, you get cos squared omega t plus phi plus sin squared omega t plus phi inside brackets, and you know it is equal to 1. So your total energy is E equal to half Ka squared. So total energy does not have a function of time. It is just a constant, half Ka squared. You know K is m omega squared and A is the amplitude or the radius of the circle or the distance from the center to one extreme position, that is capital A. So if you represent energy graphically, the first graph shows kinetic energy, potential energy and total energy as a function of time. So here we have in the first graph energy. The blue line represents kinetic energy as a function of time given by the equation half Ka squared sin squared omega t plus phi. The black line shows potential energy as a function of time, and the straight line on top of these two graphs show total energy E equal to half Ka squared. And you know total energy for any particle in motion is a constant by the law of conservation of energy. Total energy will be a constant. So that is represented by E, the straight line, the straight black line shown at the top. Similarly, look at the second graph. Here, this graph represents kinetic energy, potential energy and total energy as a function of x, as a function of displacement. So you have here the 0 represents or O represents the mean position of the oscillating particle. It goes to plus A, that is one extreme position, then it comes back to 0, then it comes back to goes to minus A and comes back to 0. So much is one oscillation. I repeat, the oscillating particle starts from here, x equal to 0, it goes to plus A, on the right side it comes to the center to 0, then it goes to minus A and then it comes back to 0. So this is represented by the blue line represents the kinetic energy as a function of displacement. So kinetic energy is maximum here, energy is maximum at the center and minimum at minus A and plus A. And just the opposite happens in the case of potential energy, which is represented by the black line. Potential energy is minimum at the center position and maximum at plus A and minus A. And total energy is a constant. It is given by the black line on top. It is uniform. It is always half K A squared. Okay, thank you students. So let us continue in the next class.